Hi, today's podcast talks about acids and bases, specifically strong and weak bases. And before we go into how to do the problems with strong and weak bases, we need to understand how and what strong bases are and weak bases are and what they look like in a container. So, strong bases are basically group 1 and group 2 calcium down. Now, here's a periodic table, and I have some examples on this right-hand side here of bases, and if you'll notice, most of them are OH, so those are Arrhenius bases. So first of all, that triggers me that I have bases, except for this very last one right here, this NH3. Okay, but that's a base. It turns litmus paper blue, so I know it's a base. So if you look, where's group 1? Well, group 1's here. We're not going to include hydrogen. Here's group 1, and here's group 2, calcium down. So it means I am not going to include beryllium or magnesium or anything in the middle here. Only these two columns, group 1, group 2, calcium down. So let's look. There's a base, right? We've agreed these are all bases, and even this because it turns litmus paper blue. Someone told me it's a base. Lithium, group 1, it's a strong base. This simple. Calcium, group 2, it's a strong base because it's group 1 or group 2 calcium down. Beryllium, group 2, but it's not calcium down, isn't it? It's not below calcium and including calcium, it's above it. So this is a weak base. What about iron hydroxide? Iron's in here. Is it in group 1 or group 2? No. So it's a weak base. What about ammonia? Well, there's not even OH on there, and it's not even on the periodic table in this format, and so I'm going to go ahead and say it's a weak base. Why? Because it is not group 1 or group 2 calcium down, and that is why. Okay, that's your strong bases. Now, what is a strong base, you ask? Well, a strong base completely dissociates in water. That means if I was to have a container that has water, sorry about that, water in it, okay, and this has water in it, by the way, guys. So this is water. All this whitish stuff is water in here. And these are sodium ions and hydroxide ions. Do you see any NaOH? Any of this NaOH particle in here? I don't, do you? So this is an aqueous container of sodium hydroxide. Let's just say it's 2 molar. That's what it would say on the outside of it. Well, you know for a fact that there's none of these in here at all. None. None of these particles of NaOH. What is there? There's only sodium ions. 2 molar of them, by the way, because it's a 1-to-1 ratio, and hydroxide ions. Again, it's 2 molar because it's a 1-to-1 ratio. Only. So the only thing floating around in this container are water, hydroxide, and sodium. And we're going to call these species, just like you have species of plants or species of animals in the biology kingdom. This is the chemistry kingdom, and those are called species. I see none of these. And what makes this strong? Well, if I have OH minus, I can find pH and POH, and that makes me strong because I have all my OH particles that are contained in this substance, and they're completely dissociated floating around. There's none of this left at all. Okay? Now, what about a weak base? Now, this container right here is strong, just like we talked about, right? A single arrow. I have none of this floating around in here at all. All I have are sodium and hydroxide ions. You see that right there? I have none of my undissociated particles floating around. So to make this easier for you, I'm going to go ahead and get rid of this. Not very well, but you get the idea. And I'm going to go ahead and look at my iron hydroxide, this undissociated particle right here. So this container would say, would have whatever molarity is on here, and this would be aqueous because this itself is dissolved as a blob. Do you see this? 1, 2, 3, 4, 5 of those. There's lots of these floating around. Have they broken apart into iron 2+ ions? No, there's very few of these. And how about hydroxide ions? No, there's very few of those. See this? These are my iron right here, and these are my hydroxide. See that? I have very few of those compared to my undissociated particle. So what's that mean as far as being a base? That means I have very few of my hydroxide ions. which means I'm going to have less hydroxyl ions to make a pH or pOH value. Right, now, what if I have my hydrochloric acid? This right here, I have none in this container. Do you see this? All I have is H plus ions and chloride ions. I have none of this HCl. Right? It completely dissociates. So if I do my pH, I've got hydrogen ion concentrations in there. And so all my hydrogen ions that are present in this container come from this HCl. What about this right here? This bicarbonic acid. Well, if I have this right here, I have blobs of this. Don't I? I have lots of those floating around. So this is going to be a double arrow. H plus and HCO3 minus. I have lots of this floating around and very few of these and very few of these. I have none of this and all of these are dissociated. So that's the big thing to understand. And there's a Ka or Kb charts, which we've looked at before. But you really need to understand this because you need to understand how to solve these problems. Now, what is this? An AOH. It's a base. It's a strong base, group 1. So my sodium's not going to matter. Even though I have this much molarity of my sodium ion floating around, I don't care about it. I also have water in that container floating around. I don't care about it either. But I do care about my molarity of my hydroxide ion concentration, right? And I need to know that because I'm going to use this to find out my pOH. So I know that this is my hydroxide ion concentration. Okay, at 5.2 times 10 minus 2 molarity, OH minus. How do I find pOH? I plug this into my pOH formula, don't I? And when I do that, what do you get? You get, let me go ahead and put this in my calculator. I get 1.28. So my pOH is 1.28. pOH. Be careful. And this is my molarity of my hydroxide ion. That's my pOH, 1.28. What's my pH? Well, don't you subtract from 14? And I would get 12.72 would be my pH. Okay, now, what's pH tell me? It tells me if I have an acid or a base. And since it's greater than 7, I know I have a base. So, I know this, I found this, and I found my pOH. How do I find H+? Well, I can do it a couple ways. I can use my KW formula, right, and plug in all the H plus and all the OH minus floating around. And that's my OH minus, isn't it? So if I plug that in and I solve, that's going to be my hydrogen ion concentration. And if I solve, I get 1.92 times 10 to the negative 13th molarity for my hydrogen ion. Now there's another way I could have solved. What could I have done? I could have taken my pH, which is 12.72, and plugged it into this formula, and taken the antilog of my negative pH. And I would have found the same thing. And this is my answer. Okay? Now, this is fairly easy because it's a strong base. What if you have a weak base? Well, how do you know you have a weak base? Well, here's a base. How do I know it's a base? Well, you'll know it's a base sooner or later. But they give me a Kb. That means I have a weak base. Remember we had Ka, that was a weak acid. But now I have Kb, so that means I have a weak base. Okay? Now, I need to find the pH. So, it's very interesting to me because when you have a weak base, or any kind of base problem, you're doing a weak base, you always take water, you dissociate, so you still do a dissociation equation, right? But if you notice what's going to happen, isn't this going to throw a hydrogen ion? I should be using red to help you out here. okay? Which means that I have NH4 plus aqueous and OH minus. See that right there? So this is what makes me my base. And I find it interesting that when you have a weak base that you add water, when actually that's what's going on with the weak acid as well. So if it confuses you, you can put that water in both cases, and I'll show you that in class. Now, what would happen on this side to make it go back? Wouldn't this be true? And this isn't what we're talking about, but this is why. This is a Bronsted-Lowry acid and base. This is my acid, this is my base, this is my conjugate acid, and this is my conjugate base. Okay, so that's why this works the way it does. Get rid of some of this junk here. Okay, now, what's true? Because I need to do this problem. What don't you include? Because I'm going to find the pH. So what did we do when we had a weak acid? Didn't we do ice? So what do we have? We have a weak base, so we're also going to do ice. What don't you include when you're doing ice because you're doing equilibrium? You don't include this right here. Okay? So I'm going to go ahead and write ICE. And what's my molarity? 15 molar. Right? And I have none of this and none of this. This is going to go down. And by the way, this is balanced. Okay? And this is going to go up by x. So here I have 15 minus x. This is x, and this is x. So I'm going to go ahead and write a Kb equation, right? An equilibrium, but it's Kb. And that's going to be equal to my NH4 plus, my ammonium ion, times my hydroxide ion, over my ammonia aqueous. No water, right? Because it's a liquid, so it's not included. And that's going to be equal to my Kb value, right? And what am I going to plug in? Well, what plugs in? I have x here, and 15.0 minus x here. Now, what did we do before? We ignored this, didn't we? Why did we ignore this x? We ignored it because it was so small. Why is it so small? Because it's coming from a very bad dissociator. This doesn't dissociate well. I know it's got a Kb value. There's lots of this, and very few of these ions, and very few of these ions. So to make my math easier, we're going to go ahead and ignore that. Okay? So when you do that, you have x squared equals 1.8 times 10 to the minus 5 times 15. And you're going to go ahead, because there's an x squared, and you're going to square root this whole entity. And you're going to come up with an x equal to 1.6 times 10 to the negative 2. Now what is that x? It's the molarity, and it's the molarity here of my OH. So this is equal to my OH minus ion concentration. So if that's true, how do we find pH? Because that's what we want to find, don't we? We want to find pH. So let me go ahead and erase some of this. Make this bigger. Make some space for myself to write here. Okay? And I can do this a couple ways, but I'm going to go ahead and I'm going to say that the OH minus concentration times the H plus concentration is equal to Kw. And I know the OH minus concentration is 1.6 times 10 to the minus 2. So to solve for H plus, I go ahead and do my math, and I'm going to go ahead and get 6.3 times 10 to the negative 13th molarity. That's my hydrogen ion concentration. And to find pH, I'm going to go ahead and plug into negative log of my hydrogen ion concentration. And I'm going to go ahead and get a value of 12.20. And that's my pH. And that tells me that I have a base because it's greater than 7. Right? Okay, so let's do another one. This is methylamine. How about that? I'm going to tell you it's a base. Okay? I'm going to tell you it's a base and it's got this formula. So I want you to find the Kb for this. So how do we do this? Let's look at some of the key points here. I have a 1 molar solution of methylamine. I'm trusting that it says it's a base because it says it's a weak base. It tells me its formula. So the very first thing I have to do is dissociate. And actually, let me give myself some more room here. Okay, so let's move this up. There we go. Okay, now, what's true? I'm going to go ahead and take CH3 and H2. I'm going to put it with water. I'm going to write water HOH so you can see what's going on here. Okay, and actually, let me go ahead and write water like this so you can see. This is my OH minus ion. Right? So what's going to happen? This is going to toss. This is my base, this is my acid. Right? This is a liquid. This is aqueous. Okay? And by the way, I didn't mean to separate these. This is actually one big compound here. So let me write it so it's a little clearer for you. This is CH3NH2. Okay? Now what's going to happen is this is going to form CH3NH3 plus. It actually catches one of the hydrogen ions and what's left, OH minus, and that makes this the space, right? And this is aqueous. This is aqueous. This is aqueous. Okay, so that's why this is happening. This is throwing a hydrogen ion over here. See that? Now, that's the acid and this is my base. That's why it's called a base. So, let's go ahead and look at this closely. What do we have to do here? What's your steps? Ignore this. Write your ICE. What do you have? You have a 1 molar solution of this. You have none of this and none of this. This is going down by X. This is going up by X. Correct? Okay, now I'm going to go ahead and what do I know here? They give me a pH. So that means my pH is equal to 12.32. What do I know? That plugs into my negative log of my hydrogen ion concentration, doesn't it? Okay. Well, if that's true, then what do I know? I know that I can work backwards and find out my hydrogen ion concentration. So what do I know? I know my hydrogen ion concentration is equal to the anti-log, second log, of my negative 12.32. And that's going to give me a value of 4.78 or 4.79 times 10 to the negative 13. And that's my molarity for my hydrogen ion concentration. Now, why is that handy? Well, I need to use that to find out my OH ion concentration. How do I do that? Well, what do? You plug in a kW, don't you? So what's kW? 1.0 times 10 to the minus 14th, right, is equal to H plus and OH minus. I'm going to go ahead and plug that in here. So this is going to be my 4.78 times 10 to the minus 13. So I'm going to take 1 times 10 to the negative 14th and divide it, and I get 0.02, let's just say 0.021, it's 0.2089, and this is my molarity of my hydroxide ion concentration. So what do I know? I know my X, don't I? I know that X is equal to this. right? Now what's that mean? That means if I know X, can't I solve for my Kb? What is Kb? Kb is equal to this ion times this ion over this methylamine. And what do I know? I know that this is X, I know that this is X, and I know that this is 1.0 plus X. I'm trying to find Kb, aren't I? I don't know that. All right, now what is X? Don't we know X is equal to this value right here? So I'm going to go ahead and plug that in. And I'm going to say that this is 0.021. This is 0.021. And this is 1 plus 0.021, which I can ignore if I want to. So I have 0.021 times 0.021 divided by, and I'm going to get 4.31 times 10 to the minus 4. And that is equal to my Kb. And that's how you do that.